Good day, everyone. On behalf of my fellow authors, I am honored to present our paper entitled Optimization of the Waste Collection Arc Routing Problem using the physics-based electromagnetism-like algorithm. So for the background of the study, one of the problematic sectors that countries all over the world face includes municipal solid waste management because it is essentially complex. There is a rapid increase of waste amount due to development, and expensive management costs are needed both in developing and developed countries. In fact, waste collection is to be treated as a primary objective in planning sustainable waste management because the existence of good waste collection is essential before investing in more sophisticated infrastructure. Moreover, negligence of this detail has been shown to undo waste treatment advantages, for example, as waste is not properly collected and disposed. With this, the study aims to formulate this problem scenario as a vehicle routing problem to optimize waste collection service in Marikina City. So several kinds of literature on collection route optimization have been written and conducted through the years. And this problem has been formulated as a vehicle routing problem, or VRP as well. So in fact, according to the literature, an efficient and effective solid waste collection can be done by system analysis and optimization of operations like planning and collection, planning the collection route. So the VRP is actually rooted from the traditional traveling salesman problem in combinatorial optimization, wherein it is classified as an NP-hard problem, which makes it challenging to solve. So the context of the VRP in this study is to find an optimal waste collection path that starts at a waste depot and ends at the same point, given a network of nodes and edges. Of course, while making sure that all of the members of the set of required streets or the set of streets with collection requests are traversed. Next objective is to minimize the cost function composed of fuel consumption and compare the potential amount of emission emitted per arc. So the static emission model for network links will be utilized to identify potential emissions that may be presented for each arc. So the equation is shown in the slide. On the other hand, the research aims to use the comprehensive model emissions model, or the CMEM, to calculate the fuel consumption for every arc. So other parameters used in the CMEM are listed in the table in this slide, which is based on the vehicle model of JAC. Of course, these values can be adjusted in the context of waste collection trucks used in the Philippines. Finding the global optimum of the problem, like the VRP NP-hard problem, or the best point of optimality in a reasonable amount of time is guaranteed using exact methods of optimization. However, when the problem size increases, it becomes impractical to use as the computational complexity to solve them increases as well. So to get through this computational limitation in solving NP-hard problems, heuristics and approximation algorithms have been used in cases like the VRP. So one example of such approximation algorithm is the EM-like. So in the study, to get the optimal path of waste collection, the study will implement the physics-based EM-like algorithm to find a solution to the routing problem. So EM-like is a population-based algorithm, and population-based algorithm start with randomly selecting points from a feasible region. So in this study, 5 initial points were considered. In the context of the study, each particle is electrically charged. That is, has a value related to the objective function value that we are trying to minimize. So as you can see here, the algorithm simulates the interaction of particles caused by the forces between them. So for example, say we have particles 1 and 2 from the initial population. So each particle represents a possible solution. So it means each one is composed of a sequence of edges to be taken on the map, such that the path will start at the depot and end at the same point while covering the required streets. So shown in the slide is the table containing the first 5 components of the path to be taken by the truck. So the columns and nodes 1 and nodes 2 are the source and target nodes respectively. So the charge of each particle, as mentioned before, is related to the objective function value, and it identifies the magnitude of attraction or repulsion of the point over the whole population. So this means that better objective function values causes higher magnitude of attraction. So as shown in the figure here, the charge 3 moves repulsively from particle 1 as the latter has worse function value. So its response, on the other hand, to particle 2 is attractive because the latter has a better solution. So this mechanism of the algorithm encourages the points at each iteration to move away from worse and move towards better solution. So the calculation of resultant forces on each particle is shown in this slide. So this procedure aims to ensure that all points move to the better points and to be far from the worst ones. So the one with a better objective function value between pairs of particles will attract the other. And the one with the worst value repulses the other. So after this calculation, the particle's movement will be evaluated, which determines the direction and step length of movement. So the movement of each particle is calculated next. So this procedure aims to displace the particles in the population according to the resultant force exerted on them. So for instance, for component 1 of the ith particle or solution, the new position according to the resultant force at the corresponding component can be calculated using the equation shown in the slide. Geographic Information Systems will be utilized to extract spatial data from OpenStreetMap by generating formatted shapefile data such as road networks, service points, and intersections. So the spatial data taken will only contain planar characteristics and is not fitting for 3D analysis. And the road network information will not give the road restrictions, real-time road closures due to constructions. However, it will contain traffic directions, road types, and street names. And of course, other data features like the multi-line string profile that specifies the location of the street in the map, speed limit, and the length of the road are calculated as well. So as you can see in here, this is the directed multigraph representation. And this shows that the road network shown in the previous slide can be transformed into a mathematical graph like what is shown in the right side of the slide. So the study incorporates the use of this representation as the algorithm will be exploring a directed multigraph-based representation of the road network, where arcs will correspond to streets and nodes will be the intersection and dead ends. So shown in the slide is an instance of the actual abstract representation of the network. So the connection of the nodes in the left are identical with the connection on the right. So for the results in discussion, so the EM-like algorithm the results of the EM-like algorithm implementation is shown in the table in the slide, and the solution gives a sequence of edges or pairs of nodes that show a valid path when traced on a geographical map. So the column initial, as you can see in here, signifies the solution generated initially to start the algorithm. So in iteration 1, particle 5 displayed optimal values So it is carried on to iteration 2, where it's still the best value despite all the particles around it changing position. So the particles should be seen as the dynamic variables. What I mean by that is that, for example, iteration 1 treats particle 1 as best, while in iteration 7, it is treated as the worst. So this means that what matters is identifying a position vector composed of a set of components that will locate the place where minimum values of the objective function values are obtained. On the other hand, the table here shows the summary of the variables for each best particle per iteration. So as you can see in here, there is a trade-off between minimizing fuel consumption by decreasing the distance taken. So although the best point holds the least fuel consumption, the number of edges or streets covered are also fewer than the particle with the highest fuel consumption. And the unique nodes row signify the number of unique arcs traveled throughout the service. The slide shows the changes per iteration of best objective function values versus the mean. So it can be seen that the best solution is slowly decreasing in value. So this slow and decrease in minimization may suggest the need to implement interventions to speed up the computational frame in getting converging solutions at a faster time or at a reasonable intervals, steps or iteration. In the slide, you can see the waste collection path that optimizes the route. So the yellow node specifies the waste depot, while the red lines specify the movement of each component of the particle. So that is, these are the visible paths. Well, on the other hand, the green path signifies the shortest path from the last node of the last component of the particle going back to the depot. So the light blue lines are the ones not covered by the waste rock as specified. So for the conclusions and recommendations, the best objective function value is seen to be decreasing, which is preferred, and because it is converging towards a value close to 4. So this means that the algorithm is moving and it encourages other particles to move towards optimal locations. So next is the generation of the initial solution can be further improved using efficiency-based path scanning heuristics, clustering-based methods to locate the best pairs of nodes that will cover streets as much as possible, or employing guided search algorithms to make informed decisions on what node to take or not. Third, it's also recommended to evaluate the performance of the algorithm through the use of artificial landscapes like test functions. And lastly, future research on obtaining Pareto optimal states of solutions can also be done, especially for multi-objective situations like minimizing emissions and fuel consumption simultaneously, as there is a trade-off between choosing only one over the other. So that is the end of my presentation. Thank you very much for your time and listening.